metamaterials has grown as a field because there's a great lacking particularly in electromagnetism, of materials to build something. If you want to make a device, a product, or whatever, you've got to make it out of something. There has to be a material available with the right properties. And sometimes those materials weren't available. The most spectacular omission was materials which had this mysterious property of negative refraction. And that was one of the early things which happened here in San Diego, the discovery or the manufacture of a material which had a negative refractive index. So there were many other things along the way, but that lit the fuse, I think. And in a way, it was an accident. So this was the paper that really started off many things. I've been working as a consultant with the Marconi company in the UK, which was a company manufacturing radar-absorbing material, sticking on battleships and so on. And they had a product that they didn't, that worked very well, but they didn't know why it worked very well. And it was out of that research, that discovering why this product worked, that came the concept of metamaterials, which is function through structure rather than function through chemistry. So you make some microstructure, much less than the wavelength. It responds in a certain way, a resonant way perhaps. And then you put these elements together and you have a material. Much the same way you put atoms together to make an ordinary material. Now, one of the things I did for the Marconi company, by the way, my wife said one day, oh, the Marconi shares seem very cheap at the moment. Why don't we buy some? So I invested all my consultancy money in the Marconi company. A year later, they were worth nothing, the company. But they got all their money back. I'm not rich because of metamaterials. Okay, so this paper is a conference paper. And there was a conference, I think in 1998, because this publication was late. Was it 98 or 99, David? 98. It was at Laguna Beach. It was PEX 1, organized by Eli Jablonowitz in Laguna Beach. It was a beautiful location, ideal for thinking and conversing and so on. And there were dolphins playing in the bay, lovely. And I talked about, amongst other things, this structure and others, but this is the one which really caught on. It's the split ring. The idea behind it was to make magnetism without magnets. So this thing's made of copper. You put a magnetic field down the middle, and as you do so, you induce a current which flows round the ring, and that in turn induces a magnetic moment, because a current flowing in a ring makes a magnet. So you get a magnetic response, even though copper, as you know very well, is not a magnetic material. There's no iron, there's no nickel in this structure. But there's something else you may notice about this ring, and that it is split. So the current can't go right round this ring. In order to flow, it's got to jump this gap. So there are two things happening here. There's current flowing around in a ring, which is an inductor, and there's electricity jumping across a gap, which is a capacitance. Everybody in this room knows LC resonator, okay? This is a resonant circuit. And one thing resonant circuits do is that, very like a pendulum, if you take a pendulum, which is also a resonant system, and it has a resonant period, okay? Just let it go and it swings with a certain period. Now, if you want to force the pendulum to drive it, you might want to move the support to and fro like that. Now, if you do that real slow, the pendulum will go where you take it. Do it real fast, like that, faster than the period of the pendulum, and the pendulum will do this. Try it. And that is an essential component of this first success we have with negative refractive index, because just as the pendulum went the opposite way, if you push it too fast, so this resonant circuit, instead of going a paramagnetic response to the forcing field, it will give a diamagnetic response in the opposite direction if you force it too quick. So you get negative magnetism. There are other structures, wire structures I talked about at the meeting, which will give negative electrical response to a system. And it turns out those are the two ingredients that you need for this thing. We're talking about negative refraction. So this is a chart I like to show. This is the electrical response, epsilon, positive response, negative response. The magnetic response, mu, positive mu, negative mu. We know all about this region here. This is dielectrics and so on. We know all about this region here. Positive mu, negative epsilon, that's a metal. Metal is opaque because of the fact that epsilon is negative. In fact, the refractive index is imaginary, which is why it's not transparent. Now, the same is true of materials with negative mu and positive epsilon. There are not many of those, but when you get them, they also are opaque. And it happens that when you multiply, so essentially the refractive index is the square root of epsilon times mu. So if one's negative, one of those is negative, n is imaginary. But if they're both negative, then you get a real number for n, but it turns out that it has to be negative. Very crudely, you could argue taking the square root of minus squared is a minus, isn't it? Well, that's not a very good argument, but it turns out to be the correct one. Okay, so that's one of my favorite diagrams here. And actually, in nature, there is no material with that property. Which brings me to this guy. This is our dear friend, Victor Veselago. He's a big Russian bear of a man. He was. Sadly, he passed away just a few years ago, but not before he'd had the chance to see the first realization of his dream, because he was a man who first took seriously this concept of a negative refractive index. Other people had sort of said, yeah, well, if you do these two things or whatever, but he was the guy who took it seriously, wrote a long paper in 1964. That was in Russian. The English version didn't come out until 1968, I think. And he explained many, but not all, of the amazing things that a negative refractive index could do. And when that paper was translated into English, he became quite famous. He was invited on a lecture tour of the USA, and a lot of luminaries like Marvin Cohen at Berkeley got interested in this because negative things have to do with superconductivity and so on. But the whole thing ground to a halt because of this fact, which I mentioned, that there are no naturally occurring materials, and search as he might, he couldn't find any. So sadly, that paper, after the initial sort of interest in it, it just sat on the library shelves and really wasn't referenced. And fast forward to 1999, because at that Laguna Beach meeting, David and Shelley Schultz were in the audience. And legend has it, but I was too busy giving the lecture, that when I said I could create a structure that had a negative magnetic response, Shelley fell off his chair. Is that true? Yeah, Shelley fell off his chair. Anyway, he survived. And they both came up and we had a chat. And they said, would you mind if we made this stuff? I thought, oh, great. We had made some in London, but we hadn't done much with it, to be honest. And it was David and Shelley who actually took this concept forward And this was one of the early papers that they wrote. So you can see that they were very soon on the job, because my paper is 1999, and we had the conversation at the conference, and their paper is 1999. So, you know, these guys get a move on in San Diego. And there's a team responsible. These are all names which some of the older people amongst you will be very familiar with. Now, the idea of this paper was to demonstrate the fact that if you had negative mu, then you have a material which is not transparent. So if only mu is negative, it's not transparent. And then they showed that in this, so in this region here, if you have no wires in the structure, you just have this magnetic thing. There is very low transmission in this region here when mu is negative. Am I getting this right, David? Thank you, very good. And then if they add the wires, negative times negative is a positive number, square root of real number, and so the thing should be transmissive again. And this paper showed that that did happen. Now, none of us knew about negative refraction at that time, and I believe it was the referee that pointed out. What is that? What's the story, David? The referee?
Yeah, the paper was rejected initially, and we did a literature search, yes, and found that paper.
Okay, I think it was Willie did the research, was it?
Yeah, he went and looked and discovered it. Yeah.
Yeah. Anyway, so industrial archaeology, right? This paper of Veselago's was unearthed, and so then it was realized that this was not merely not merely a real refractive index, but actually the sign of the refractive index was negative. So these guys have made something which is really, really weird. Now here's a photograph that I took when I was on sabbatical in San Diego. It's not the one where they did demonstrate negative refraction, but I think it's a pretty good photograph. So anyway, that's what you're seeing. And this shows a structure which exhibits negative refractive index. And you can see that although they squared it off, this is identifiably a split ring. What's harder to see is this shadow here, and that's a wire. And that, in contrast to the rings, which have a magnetic resonance, the wire has an electrical resonance. Not surprisingly, it's a dipole, isn't it? So you have negative, if you tune them right, you have negative mu and negative epsilon. And that paper was then reported in Science. And that created a lot of interest, a lot of excitement. And that really, it was like lighting a Roman candle or a rocket. Things really took off after that time. Now, let me spend a little bit of time explaining why this is such a crazy thing to have a negative refractive index. We know Snell's law, and if one of these angles is negative, then you have a negative refractive index. Now, a positive index material would have the ray coming this side of the normal. If it's glass, it will be bent towards the normal. So this is a positive angle, and if you get an angle going this way, then that counts as a negative angle. But already you see something a bit crazy going on, because this is where the rays go. So if you made a little packet of waves and you sent them at this negative surface, they would go down the red route. But there's a sort of iron law from mathematics, not physics, which is that if you have a flat surface and you have a wave vector, which is how the waves behave, not the wave packets. Okay, there are two velocities, a group velocities with wave packets, and there's a wave velocity, which is where the waves go, and they don't have to go the same place. They usually do in air or glass, but they don't have to, and they don't in negative materials, because the rigid law is that the component of the wave vector parallel to the surface must be conserved. So the wave vector cannot obey that law if it points in this direction. It has to point in that direction. What does that mean? So if we make a wave packet here, the wave goes this way, the packet goes this way, and the waves try to get out to the other end of the packet. Now there are other waves that look like that. Never before this time electromagnetic waves. You can make water waves, I believe, I've not done it, in which you have the waves and the packet moving in a different direction. To try chucking stones in a pond, maybe you'll see it, but this is quite unusual behavior, and it is a first indication that something is really significantly different from what we're used to in electromagnetism is happening. But not everybody liked it. Indeed, these three gentlemen of Texas wrote this paper in Phys Rev letters. And I think what it should, I mean, this is the start of a long series of arguments which took place over negative refraction and other things. And I think it further emphasized the point that negative refraction is rather a subtle thing. Now, these, particularly Professor Walser, was a very highly respected scientist. He has lots of contracts, I think, with the US military. Very highly respected. And there they are saying it can't exist. So, really smart people have failed to misunderstand the consequences of negative refraction, because it does exist. The experiments show it exists. So why is this so difficult? Well, not only did they disagree with us, they were very angry about it. So angry that it required capital letters, red ink, exclamation marks, underlining, bold typeface. Okay, very exciting. I think this has been deleted from their website now, but it was there for many years after everybody thought there really was negative refractive index. Where did they go wrong? So let me try and summarize their argument. Now, one of the ways you can tell what the group velocity of some set of waves is to have two waves. So what I've done here is to have two waves of a slightly different frequency headed in the same direction. So the waves are going this way, and now this is a packet of waves formed by the interference between these two different frequencies. And you watch how fast these black marks here, the interference pattern, how fast that moves. And that's the group velocity. Of course, it's the differential, two slightly different frequencies, the differential of the frequency with respect to wave vector. Okay. Now, if you try to superpose these at the surface, you see here are the waves coming in this direction. So the blue lines are the interference pattern. These are not the wave fronts. This is the black drawn it in blue here. This is the interference pattern, and because the waves are traveling in this direction, the parallel component is in this direction. Now, if you have negative refraction, the waves, the group velocity is in this direction, and so Walser would expect that the interference fronts move like this, indicating the direction of the group velocity. And that inevitably leads to a parallel component of the group velocity in this direction. And just as you have to match the wave fronts at the surface and conserve parallel K, these interference patterns have to move lockstep in one another. Of course, if they don't, you can't possibly match the fields at the surface. That was the Walser argument. It seems pretty watertight, doesn't it? So there was one time when Shelley flew me over from London, and we're all sitting in the basement where Shelley's office was in the physics department and scratching our heads and saying, this has got to be wrong. We know the experiment says it's wrong, but why is it wrong? Well, after much debate and so on, we finally realized what was going on. It's really quite subtle. And it has to do with moire patterns. So what we've been talking about is waves of two different frequencies heading in the same direction. And then that really does show you the group velocity. But have you ever fiddled about with two transparent sheets and made this funny pattern they make when they overlap, but they don't quite overlap? It's called a moire pattern, maybe you know. So what I've done here is to take this pattern and I've slightly, a couple of degrees maybe, rotated the orientation of the wave vector. And you can see that this very slight movement of the angle changes the angle enormously. The waves and the groups are still heading this way, but the wave fronts appear, if you draw the normal, to be heading that way. But it's a false story, because this is an effect of the moire as I rotate. Now, why does that matter? It turns out that one of the laws which negative refraction has to obey, and you get nonsense if you don't have this law, is that the refractive index has to disperse with frequency. So if we go back and look at this wave here, and then have a second wave at a slightly different angle, the refractive index will, at a slightly different energy. So it's going in the same direction, but a slightly different energy. Then because of the dispersion of the refractive index with energy, Snell's law will tell you that the angle will change. It doesn't have to change very much, as I've shown you, because just a degree or two will completely disorient the moire pattern. And it's enough so that when you rotate the moire pattern, as it has to be because of the dispersion, then you get this picture here. The waves are still heading here, but now the interference fronts, because the waves are not traveling in quite the same direction, the interference front looks this. And so you get the group velocity showing negative refraction, and you get the parallel motion of the interference fronts in the same direction. So problem resolved, okay? Whew, big relief. Okay. Well, time for another negative story, I think, before I'm done. This is another example of what can happen. So this rediscovery of negative refraction and experimental realization got me thinking, and the story I've told many times. So I was head of department at the time, this was year 2000, and heads of departments, as they will tell you non-stop, are very busy. So during the week, I didn't do much research. My research was done at the weekend, and particularly if I couldn't go out in my garden, which was the case on one wet Sunday morning. And I sat down and I looked at something called the Veselago lens. What Veselago showed that if you had negative refraction and you negatively refract from a surface, you bend the light into a sort of chevron, and that's exactly what a lens does. So negative refraction can focus light. Actually, it has two foci, because you get, if you have a slab of stuff, you have negative refraction going in and then going out. So you get two foci. And it was regarded as a curiosity. We got lenses, we don't need another one kind of thing. And it's well known that lenses have this restriction in the resolving power. It is thought to be a rigid law of refraction, diffraction rather, that with a microscope, with regular lenses, you can't see anything smaller than about half the wavelength of light. And that's really, really troublesome. Biologists want to see inside cells. Cells start about half a micron, and you can't see the stuff inside unless you have some very, very special microscopes that use nonlinearity and all that sort of thing to enhance the resolution. But I took another look at the Veselago lens, and I thought, hey, it does some really rather cute things. It doesn't distort in some way. It doesn't do this, doesn't do that. It's really quite beautiful and perfect. Is it perfect? Nobody tried to show. So it was a very easy calculation. Maxwell's equations match at 2 interfaces. Okay, it's about an hour's work. Any third-year undergraduate student could do it who had a course in Maxwell's equations. And the focus was perfect. I was kind of horrified because I thought the focus wouldn't be perfect in accordance with Abbe's law, which says it can't be. And I was alarmed because I was expecting it not to be perfect, but for an interesting reasons. Of course, I had other arguments, rather mathematical ones, that it should be perfect. So I went to my friends before I revealed it to my enemies in physical review letters and said, I have this result. They uniformly said, it's wrong. Okay, I said, you're a friend, tell me why it's wrong. Well, it disobeys Abbe's law. Right, okay, what else? Okay. So after 3 months of dialogue that went pretty much like that, I took the step of publishing it. And yes, no, oh dear, after all the work, there were, I won't show you to them, but there were also plenty of capitals, bold, colored, whatnots. Dear, dear, dear. So you can see it's not been an easy ride for David and myself. And those are just 2 examples of the, well, you know, what doesn't kill you makes you stronger. So I'll finish my part of the story then, hand over the lectern to David.
It is awesome to be here back at UCSD. It's really a UCSD story because this happened in physics and a whole series of incredible events that transpired. Of course, working with John Pendry was an incredible opportunity, but we had great people at UCSD as well. My advisor, Sheldon Schultz, but many other people who were in the department were really fantastic physicists, really supportive. And at no point was there a case where I was worried, and John talked about all the controversy. We had plenty of support from really great physicists like Marshall Rosenbluth and Don Fredkin and Norman Kroll and Dmitry Basov, who were like, yeah, what you guys are doing are right. Sian Emmett Nasser was in the mechanical engineering department, also helpful in the early days. And along the top are some of the people that were in Shelley's lab and I later worked with, who contributed: Willie Padilla, Tony Starr, who happens to be here, Dave Schurg, who happens to be here today, and Jack Mock. So really, it was great that it happened here. And John has given really a lot of the discussion of the history. So even if I touch it, I couldn't really repeat it. But what I'd say is, from my point of view, I was a postdoc, kind of had just not too recently, not very long after my PhD, working in Shelley's group as a postdoc. So all of this was done really not my main job at all. It was something that was just done out of interest. And to the students, I'd say, especially in physics, you can go a long time feeling like you have no value, and maybe the things you're working on have no value. But the reality is you don't know. No one would have predicted this. And this is really the power of an idea, the power of some basic physics thought has really blown up into what is a very big deal. Metamaterials is now a major pursuit. And it all started with really simple and almost ideas that you would have never gotten them funded, you would have never gotten them published. So just to start out, yes, I was really interested in John's work. He had published this paper on, with a tantalizing topic, extremely low frequency plasmons and metallic mesostructures. And really it was just metal wires and the idea that you could have a bunch of metal wires and they would act like a plasmonic medium, a medium with negative epsilon. And so that was interesting. And back in 1996, I started thinking about how we would make this and play around at microwave frequencies and started playing around with wires. I was at a meeting in France, and Eli Jablonovich had also become really interested in wires. And he said, hey, I'm going to have this workshop in Laguna Beach. Why don't you come and talk about plasmon media? And I said, I don't know anything about plasmon media. I know, some other stuff, but not that. And he said, no, whatever you have, just come and bring it. And as it got closer to that conference, I was really, delaying. I had other things to do. And I said, I kept calling him up saying, I'm going to do a different topic. And he said, no, that's boring. Do the wires. So he kind of forced me, and I'm very grateful that he forced the issue. Eli Jablonovich is the father of photonic crystals and photonic band gap structures. So he definitely had a lot of influence. So I made it to this conference, and that's where I met John Pendry for the first time. And I had shown him a wire structure that I developed asked him if it was correct or if he thought it was correct. And he very graciously sat down with me and he said, yeah, it seems right. And then he gave this talk on what has now become this paper on the split rings, the very famous split rings. And the paper wasn't out yet. It was just his talk. And I was sitting next to my advisor, Schultz, and he described these rings and that they could have a negative mu. And it's absolutely true. Shelley nearly fell off his chair. He was like, there is no such thing as negative mu. I don't know why he said that because, it turns out there is. But he was very, very excited about this prospect, and it definitely attracted his attention. Didn't know how to do it. I just saw John's slides, but I was lucky enough to get this paper to review after the conference. And so when I received this paper, I wrote to John and I said, would you mind if we start working on this? This was sort of a blueprint on how to do it. And again, very graciously, he said, yeah, sure, go ahead. So this was the sort of structure we made. And when I say we, it was Willie Padilla. John had a couple of ideas. One was Swiss rolls. And those Swiss rolls involved rolling a lot of, like a foil around to make a Swiss roll. And these structures were really good for megahertz frequencies, which is a huge wavelength. So Willie was an undergrad working in our lab at the time, and he was rolling these Swiss rolls, and he had rolled like, a few dozen. And he said, okay, what do you think? And I said, those are great, but we're gonna need 100, 200 more. So he went and he came back and he said, I think I can make this other structure that John Pendry has in his paper, these split rings. And I said, all right, same to me. So he actually produced these split rings and they look great. And so we had a little chamber that we could use like this to do scattering experiments. So we put this sort of structure into this device here, sent microwaves in. And the basic idea of the experiment, as John explained, was if you have a negative mu, you should have an opaque material. So you should just see reflection. If you have positive mu, and epsilon is positive in both cases, you should have transmission. Very simple idea. So that was the nature of the experiment. And we did the experiment, and that's what we saw. Okay, agreed perfectly. However, if you were argumentative, you might say, well, maybe it's not that at all. Maybe it's a negative epsilon and you're just misinterpreting something. So we wanted to publish this, and desperately trying to figure out how I could break that symmetry or do something. There would be other ways to do it, but this was not our main job, so we were just trying to use whatever we could. And so that's when the thought occurred, we know the wires, this plasmonic medium that John had brought to us, has a negative epsilon. Why not combine the two? And if they don't interact in some other weird way, where it should reverse this picture, where epsilon is negative but mu is positive, you should see opacity. And when mu is negative and epsilon is negative, you should see a passband. And in fact, this is kind of summarizes it here, so that if epsilon and mu are both negative, again, you have a transparent medium. So that was the idea, add wires to the split ring resonators. And this was the experiment that did it. And it's a simple idea. All we were trying to do was prove this conjecture that the rings would have a negative mu, this region, this effective property. However, inadvertently, to do it, we had created a medium with a negative epsilon and a negative mu at the same time. And I was not aware that that was anything unusual or important. It just was kind of cool. And so we started thinking about that. But this I wrote it up, and we sent it to physical review letters. And got it back probably within 2 or 3 days with a letter that said, this does not appear to be important enough for phys rev letters. And I can't disagree with them, because I didn't even know what this could be good for. So I was talking with Willie, and I said, Willie, let's look around. So I typed into a search engine at the time, or the library, negative epsilon, negative permittivity, negative permeability. And one paper came up, and that was this paper by Victor Veselago, now the famous paper that had the title, Electrodynamics of Substances with Simultaneous Negative Values of Epsilon and Mu. It had never been referenced, never been cited. So we got that. Willie was actually the first to see it. He came in shaking into my office, and he said, I can't believe this, we've made this. Because this paper was beautifully written. It really discussed all the crazy things like the reversal of Snell's law and reversal of Cherenkov radiation, and all these things that physicists would love to think about, all in that paper. And we had just actually made the thing. And so took this and rewrote the abstract to the paper, and it was subsequently accepted into phys rev letters. And this is really the negative refraction was sort of the hallmark of what a negative index medium would be. So we had created an artificial material. We had created rings and wires, but we hadn't called it a metamaterial. But that term came from Roger Walser, who wrote this paper in some sort of, I think it was a SPIE or something like that. It's an SPIE conference. Right around the same time, right around 2000, and he coined the term electromagnetic metamaterials. And he was thinking of very different things, sort of magnetics and stuff like that. But really that term turned out to be a good buzzword, very good buzzword. Such a good buzzword that my advisor, this was our paper, by the way, and this, my advisor connected what we were doing to that term, and also discovered there was a DARPA program on metamaterials that was brewing. And so it was Shelley who said, okay, what we have is the world's first metamaterial. And that is what came into this first paper. And you can see right at the end of the abstract, metamaterial made it into this paper. So it was really the first scientific paper that used the term metamaterial. And really, that term has caught on like wildfire. Almost instantly, but it was truly something that just moved quickly. We went and presented this at the American Physical Society, and we arranged a press conference. First time I'd ever been involved in anything to do with press, at a press conference on something like this. Absolutely scared to death. For any of you who knew Shelley, you knew that he was fearless and believed this was completely deserved, had no trouble saying this was the discovery of the decade. And I was just absolutely paralyzed with fear. Somehow we made it through. The press is very interesting on science. They have trouble with it, and so we ended up with this with headlines like this, which are not our fault. Left-handed materials said to reverse energy. I don't even know what that means, but I was with the reporter, Joel Aschenbach, when he was writing this, and he said, the editor wants to use this title. Is it right? And I said, no, it's not right. And he got back on the phone. He said, he's running with it anyway. So that's how the press works. It just kind of blew up from there. We had a lot of interest from the press. I don't know why. And then when Sir John made this prediction, it went even more crazy. The idea that you could have a perfect lens and all the understanding and misunderstanding that resulted from a paper like this really blew things over the top. So as John mentioned, we had all sorts of papers questioning everything about this. And it played out even in the popular literature. I was a postdoc at the time, remember that. And people sometimes ask me, were you worried? What was this like? It was great, fantastic. If you're a postdoc, not so good for John, maybe, but if you're a postdoc and you're in the middle of a controversy about your work and everyone's taking notice, that's great. So I felt like I was in a no-lose situation. I mean, yeah, this was really good. It was nerve-wracking, but I felt like we had we knew what we were doing, so not too worried about the outcome, but it was something. And of course, there was this sorts of thing where people were attacking every little bit of what we did. And in reality, they had some reason to, because we did this experiment on the cheap. There were a lot of issues with it, but subsequently we fixed things and got better. So I won't go into this because John described it, but I'll say there was a program, DARPA was so concerned about this that they gave Boeing a program to really just prove whether negative refraction existed or didn't exist. So they paid them to recreate what we did at UCSD at a better level. They did a better design, things like that. But in the end, they just repeated the experiment more carefully and with a better sample, and again, proved that the refraction was negative. And this took Boeing and a big team to do it. And in the end, John got the last word, positively negative. So that sort of settled the controversy. So just a couple of pictures. This was such a big deal in these early days. DARPA held a summit in DC. And here you can see some of the luminaries. Here's a young Nader and Guetta, young all of us. On the left, you can see Shelley with Victor Veselago, Willie Padilla there. Shelley's up in the top. And this really, they tried to bring everyone together to say, is this real or not? They took it very seriously. Shelley even carted up our entire experiment to DC. He packaged it up in a big crate and sent the vector network analyzer or the scalar network analyzer, all these things, in an experiment that Tony helped design, showed that you could transmit some music. So you actually had some bandwidth, and so that little thing was a pickup. And as you moved it around on the negative refraction side, you'd hear the music. So it was kind of an interesting thing. But that was really, about the time when the controversy was settled. So I just now wanted to go, this is a history. Where it went from there, it got even larger. We went, when I got to Duke, again, working with John's ideas, we came across this invisibility cloak. Invisibility cloak was just a way of describing what the fields were doing. It was interesting. I didn't think anyone would take it seriously, but they did. They took it very seriously, not in a bad way, but just in a way that was in an inspirational way. So we were able to do these kinds of things. Now we're getting very good at making samples. This is an actual sample here, and you can see that this is actual field maps. And it's not so much the experiment, which was a very modest experiment, but the idea of it ended up catapulting this all over the place. So when the cloaking stuff came up, literally we were on the cover of every single newspaper. I mean, I just got tired of pulling these down because, when you hit the New York Times and USA Today and all these things, it's just a lot. And it really was an amazing ride. We were on the Today Show, mentions of it on just every show, sometimes jokes, but that's all right. Things like this. Dave Sherg up there, that was his third interview on Fox News at the time. So it really hit the high note of hype at the time. And twice on the Big Bang Theory, you can see that there's been mention of metamaterials here. You can see Veselago's diagram on one episode. And then I just noticed while I was watching the show one time, the cloak on another show. So getting on twice on the Big Bang Theory is good. And then Jeopardy. Watching Jeopardy, up comes this clue. Duke University has developed a prototype for a cloak that grants this power just like Harry Potter's. And the contestant actually got it right and won $200, which was about all metamaterials were actually worth at the time, despite all the hype. The question in my head right around then was like, gosh, this has gotten so out of control, so huge. We really need to start transitioning this. And this stuff kept coming, just more recently, here's a character on The Boys that has a carbon metamaterial skin, makes him invisible. So it really is kind of seeped in, and also into the literature, also in books and textbooks, this concept of our experiments that were done at UCSD and going forward has really become part of the fabric now of what's out there. So how do you make this thing useful? So I'll come to that. In my lab, we started getting involved in more practical research, and I also started working with a company called Intellectual Ventures. So this is a long story. I'll kind of skip some of the things we're doing, but I'm going to skip to this guy, Nathan Myhrvold. Some of you may or may not know who this is. He was the former CTO of Microsoft, but he's actually a physicist. He did his postdoc with Stephen Hawking. He had started a company around 2004, maybe a little earlier, called Intellectual Ventures. And he was reading the papers that were coming out, and he actually got attracted by all of the controversy. And so he had Intellectual Ventures take a stake in all the intellectual property that was coming out of UCSD at the time and Duke, and really made that a centerpiece of what Intellectual Ventures was. Really an important person when it starts when the topic becomes commercialization of metamaterials. And there's a few people involved here that some of these faces may look familiar, some not, but these guys here were really behind the commercialization of what I've just shown you. We had this big explosion of science and then popularity and things like that. Where do you take it? We wanted to take it into things that would actually change people's lives. So these guys really deserve credit. Most of them won't be known. Bill Gates, of course, very well known, and Nathan Myhrvold, and both of them became big fans of metamaterials. And to that end, we ended up spinning out a bunch of companies. And I gave a colloquium here once before with Shelley Schultz. And I remember a question that Jorge Hirsch asked at the end of the colloquium. He said, "How is this going to be worth $1 billion?" So as it turns out, just a few months ago, there was a combined total investment in these spin-off companies of over $1 billion. So I am able to answer that question now. This is how. All of these companies are doing various types of products, and just to give you some sense, this is Kymeta, the first company that was spun off, is making antennas for satellite communications. Another company, Echodyne, is making radar, and products are out there. These companies are quite large. There are literally thousands, if not tens of thousands of engineers just in these companies and similar that are really doing all the systems and engineering needed to make metamaterials work. So there's a whole back end of things that have to occur, electronics, programming, everything else. And so a lot of people know about metamaterials. Another company called Pivotal has these products as well. So that's the story. It's a very quick, hopefully under 15 minutes or so. idea of the trajectory of going from the lab and something that no one would have funded or thought was valuable to something that became $1 billion worth of value and climbing. And all of it is physics motivated. The inspiration was physics oriented. Physicists were behind this. It was just an incredible honor to be able to work with people like John Pendry and the physicists around here. Also, because I'm here, I can say thank you to people like Jorge Hirsch, who I actually took classes from, and part of my knowledge base comes from the people sitting here. So I'll stop there, and thank you for your attention.
One naive question. All the photographs show these nested rings, usually just two, but when there's an array of them, they're all pointed the same way. Is that for like polarization or something?
Well, yeah, so it's a tensor, right? And so these will give you properties in one direction. So if you look where the magnetic field is threading the rings, that's going to give you a response in that direction. And we would do that because it starts to get more complicated. The negative refraction experiment we did for science had rings in two directions. And the picture that John showed had the rings like this and this. If we put another one like this, then we'd have an isotropic material. But most of the times we didn't need to do it, and there's other interactions that start happening that make it more complicated. So it was really done to kind of make it as simple as possible to show the effect we were looking for.
Okay, so quote, out in nature, if it was unpolarized radiation coming in, you wouldn't get such perfect...
That's right, yeah, but we can design for that, but we had everything under control at that point.
Thank you for a fantastic talk, both of you. A couple of quick questions. I was wondering, it wasn't clear to me whether John knew about Veselago's paper before you guys found it. And the second question was a follow-up on my billion-dollar question. Is there anything on the market already, in the market?
Yeah, I'll start with the second question. The second question was, is there anything on the market? And yes, there's lots on the market. We've spun off about a dozen companies. One of them's gone public, Evolve, which does security screening. So if you go through Disneyland or Universal or sports stadiums, you're walking through one of these products that we spun off. These three companies that I've just shown here, Chimeta, Echodyne, and Pivotal, all have products that are selling in the field.
Like antennas, or what are the...
Antennas and radar systems, sensors, and imaging. And then his other question was, did you know about the Veselago paper before all of this?
No, I didn't. None of us did. It was Willie's research, as David described, in the library. I should just add, with respect to products, that the concept is diffused beyond electromagnetism. The acoustics community is taking it up enthusiastically. There is a product made in the UK which uses the metamaterial concept to make an acoustic screen. And these things, normally if you want to keep sound out of a place, you want a big, thick, heavy wall. There's some building regulation which says if you want so many dB, it's got to be so thick. This screen is so light you can wheel it around in a hospital. That's what it's designed for. It's designed to screen sounds from sick patients who can't tolerate noise. And that's on the market right now. That's just one thing. There are also applications in MRI and many other areas as well. It's just that the whole concept applies not just to electromagnetic waves, but to waves. In fact, I have a former postdoc who proposed cloaking from earthquake waves. And he actually got a petroleum company in the south of France to take thumper trucks around a metamaterial structure in the earth to show that you could guide earth waves away from obstacles. You wouldn't want to use it in New York, but you might put it around a nuclear power station.
Yeah, a very naive question. So I have a question about the invisibility cloak. So it's very frequency specific, right? And it depends on the gap, I guess. So are there these made in invisible, or they just work in like the radio wave range?
This was just in the radio wave range, and this one shown here was somewhere around 6 gigahertz. And they are very, very narrow bandwidth, and that's a necessity because of dispersion and really because of the speed of light. So it's a very limited form, but it proved the point.
Is there a possibility to create like a broadband invisibility cloak, or that's like not possible?
There's a sort of violation of the speed of light because light has to go around a longer path than as if it had traveled through free space. John's talked about this before, so that is manifested in the reality of dispersion that you have to have in a material. So that constraint doesn't occur for things like acoustics, so like an underwater cloak, maybe broader bandwidth. So there's other possibilities, but EM is a tough one.
It's not all that narrow band, though, is it? I mean,
it was pretty narrow band.
Okay, maybe one more question.
Sir John, could I ask you to expand a little on the? I guess where the negative index lens went. I'm just curious on if that has panned out. Has there been? Do you know if there's experiment revolving around it, and so on?
help me with that.
Has there been a follow-up on the perfect lens? Has there been experiment? Where's it now?
Yeah, sorry, I had a last slide I should have shown you. Some immediately after, not immediately after, but within a year of the idea of the perfect lens, George Eleftheriades in Toronto did demonstrate it with an RF rig-up. Of course, what people really wanted to see was something at least close to visible frequencies, and that was realized by Jiang Zhang somewhat later, because obviously the details of materials at these short wavelengths are more difficult. I should have shown that slide in which they demonstrated a resolution of λ/6, which is better than you can achieve with a microscope. These days, the technology is exploited again here in San Diego by one of your colleagues called Xiaowei Liu, who works on super resolution microscopy. And the way they do it there is sort of upside down, because they use something called structured illumination. So there are two sides to the microscope. Normally you're only at the end where the light comes out, but you can also structure the light that goes in. In the most elementary form, you could imagine a point of light scanning like a TV raster. But you can have more complicated patterns, and Xiaowei does this using something called a hyperbolic metamaterial. It's just half negative or whatever. And he gets very, very high resolution of biological quality. So it's difficult, it's a big challenge, but people are making progress. Thank you.
Okay, any last words from our speakers, or anything else you want to?
Any last words? Any last words?
Well, I think a big thank you to UCSD for all these creative people that you've nurtured within your institution. It's a real credit to USD, and thank you, because I don't think I'd be sitting here today as a recipient of the Kyoto Prize without the work of all the experimentalists who've made a realization of the dreams, theoretical dreams, which Veselago and I had those years ago. Thank you.